Hi class, we are now on 10.3. This is describing gases. So in the previous lessons, we saw how the properties of solids and liquids depend on the forces of attraction between particles. In this lesson, we shift our attention to gases. In a gas, the particles are spaced far apart. They move freely, interacting very little with the particles around them. Gas particles travel in a straight line until they bounce off another particle or off the walls of a container. Think of something like playing pool. If you hit the balls will kind of go in the direction until they interact with something else. And if it's hard enough, if the ball's going at a speed that's fast enough, it'll bounce off. With gas particles, they move very quickly and they continue bouncing, and then they just go in the opposite direction. So let's take a look at ideal gas. When describing gases, we often assume that they are behaving as ideal gases. An ideal gas has two key properties. The volume of the particles is much, much less than the volume of the container, and the particles have no attraction to each other. When they pass each other, they do not slow down. When they collide, they bounce off each other like billiard balls. When gases behave this way, we can predict their behavior mathematically by using simple relationships between temperature, volume, pressure of the gas. Excuse me. We commonly describe gases by the pressure they exert on their surroundings. Formally, pressure is defined as the force that is exerted divided by the area over which it is applied. We can think of pressure as the push that particles exert on everything around them. For example, this image represents gas particles within a box. These particles move freely around the box and collide with the walls of the container. Collectively, these tiny collisions create a larger push. This is the pressure on the container. With a container like this rural propane tank, the gas inside the tank exerts a pressure that pushes out on the walls of the tank. At the same time, the air outside the tank is exerting a pressure that pushes in on the walls of the tank. So there's pressure on the outside, there's pressure on the inside. We actually have pressure on us from the atmospheric particles in the air. We don't feel it, except for when our ears pop. Like when you're trying to get out of an airplane, that's when we deal with an imbalance of pressure from inside and out on the outside of us. And by us trying to pop our ears, we're trying to get that balance again. That's the only time you're really aware, and you may not even, they talk about pressure, but you didn't realize what was happening. Gas pressure is a normal part of our lives. Earth's atmosphere exerts a pressure that is essential to life. Subtle variations on atmospheric pressure cause wind and weather patterns. Pressurized air in tires keeps vehicles rolling smoothly. The bounce of a basketball is caused by the compressed air inside it. Air conditioning systems rely on the compression and expansion of gases under different pressures. Pneumatic tools use compressed air to produce a powerful force. A barometer is a device used to measure atmospheric pressure. A classic barometer is shown here. In this device, a long tube is filled with liquid, which is usually mercury, then turned upside down in a reservoir of the liquid. Gravity pulls the liquid down, creating a vacuum at the top of the tube. So you can see right here. At the same time, pressure from the outside is pushing down. At the same time, pressure from outside air pushes the liquid up into the tube. The higher the air pressure, the higher the liquid is pushed in the tube. So if we're dealing with a lot of high air pressure, this pushes us down. This liquid goes up in the tube. When it's low pressure, this pressure is not as strong. It releases some, and this liquid will come out of here and fill up more on this side. So we measure the pressure of the atmosphere by measuring the height of the mercury inside the tube. Because of this, atmospheric pressure is often reported in millimeters mercury, abbreviated mmHg. This unit is also called a torr. At sea level, the average atmospheric pressure is 760 millimeters mercury, or 760 torr. So basically, these are equivalent to each other. So let's say I'm just going to throw a random number out there. Let's say you have the air pressure is 500 millimeters mercury. It's also 500 millimeters torr, because they are 1-to-1. They're equal to each other, but they are two different units. A barometer works like a drinking straw, like drinking from a straw. When you pull the air outside of a straw, when you pull the air out of the straw, you lower the air pressure inside the straw. Because the pressure outside is greater than the pressure inside, the liquid gets pushed up into the straw. A barometer works the same way. So why do barometers use mercury rather than less toxic liquid like water or oil? Because mercury is 13 times more denser than water. Atmospheric pressure is enough to push a column of mercury 760 millimeters into the air. If we used water in the barometer, the column would have to be over 33 feet high. Of course, there are many other designs for pressure gauges. The shapes and styles of these gauges differ based on the application. For practical applications, we sometimes refer to the gauge pressure of a compressed gas. The gauge pressure is the difference between the compressed gas pressure and the atmospheric pressure. For example, if the gauge on an air compressor reads 0, it doesn't mean there is a vacuum, meaning no air inside the cylinder. It means that the air pressure inside the cylinder is equal to the air outside. For the problems in this chapter, you can assume that the pressures given are absolute pressures, not gauge pressures. We can use many different units to describe gas pressure. A common unit is atmosphere, based on the standard air pressure at sea level. One atmosphere is defined as 760 millimeter, or 1 atmosphere is equal to 760 torr. Excuse me. In the United States, pressure is often described in terms of pounds per square inch, which is PSI. A basketball has a gauge pressure of about 8 PSI, while the tires on your car likely have a gauge pressure of 30 to 40. Other common units of pressure include kilopascal and the bar. For the sections ahead, you should be able to convert between these units of pressure. So these are all very good conversions. I've also given you in a handout that you guys should have printed at the beginning of the semester. There's one whole page on gases, and it has all the conversions and so forth that you need. So let's do some problems. Gases are particles spaced far apart, very little interaction between particles, and they move very, very quickly. They bounce into something, they just turn in the opposite direction and continue going. Ideal gases is a volume of that has two things you need to remember for an ideal gas, which is how we label gases, how we look at them, and how we can calculate if we believe these these two things. Volume of particles is much less than the container, and particles have no attraction to each other. Because if we didn't believe this, then we couldn't use the simple calculations. So I did not, let me just jump into this one. An automobile tire has a pressure of 31.0 psi. What is the air pressure in atmospheres? You have the conversion there. I did one of these only, and the rest I just provided the answer because by now you should be able to figure this out, just given the conversion. And it is 2.11 ATM. ATM is the easiest one to use. They're all equal to 1, and these are all 1 atmosphere equals this, 1 atmosphere equals this. 1 atmosphere equals 760 millimeter mercury, or 1 atmosphere equals 760 torr. So torr and mercury do not go together. These are two different units. I don't know why they just didn't make one more barred. If I had caught that, I would have. 550 millimeter mercury, the answer, you have a conversion to do the math, is 10.6 psi. 1.50 bar equals, 150 kilopascal. An altitude of 8,000 feet, water boils at 91.9 degrees Celsius. Why is this? Well, first of all, water boils at 100 degrees Celsius at sea level. Once you start going either up or down, then the temperature is also going to change because of the fact that it has to deal with your atmospheric pressure. To give you an idea of what this means, I found some pictures. So the atmospheric pressure at higher altitudes is lower. So that means that we deal with higher pressure the closer we get to sea level. We have more molecules in the air. We have there's more atmospheric pressure. However, when we start going up, there's less and less. That's why there's less oxygen as you start going up, hiking in a mountain. There's not as much particles up there. So you can see this is another. I found these two that kind of give an idea. It's really dense, but we're used to it. We don't feel the pressure on us. But as we start going up, the pressure is less dense. So the temperature boils at a different temperature because there's not so much atmospheric pressure to deal with. So the atmospheric pressure at higher altitudes is lower, and I'm not going to go into more of that unless if you have any questions about this, feel free to ask me. But I don't want to confuse you any more than you probably